Hi guys, this is Abhirup Karmakar. Today I will discuss about Higgs mechanism. As you know, in 2012 we found Higgs boson in LHC, but the actual Higgs mechanism was proposed much earlier in 1960s 70s by Higgs Englert. So this is a very much profound subject, and today I will discuss it not that standard model thing but from a scalar field approach. So this is very much simple. This is also called abelian Higgs mechanism. Basically the gauge fields are abelian here, that I will discuss, but in standard model there can be non-abelian gauge fields also. So with no delay we will start discussing. So to discuss Higgs mechanism, the first thing we have to know about the spontaneous symmetry breaking and Goldstone bosons or Goldstone fields. So I assume you know the basics of classical field theory, and I assume that. So basically this is a simple Lagrangian of a complex scalar field. As you can see, this is the kinetic term and this is the potential term, and we take the potential to be this. So this is a potential of phi 4 theory. We are considering phi 4 theory. So then uh, what is the classical vacuums or vacuum of the theory? That is basically setting this potential to be 0. We get this simple thing that mod phi square is a square. So as you can know that there are infinitely many classical vacua in the circle in the complex plane. So this is a circle in the complex plane, so there are infinitely many classical vacuum. So you choose one of the classical vacuum that we are choosing phi equal to. So this is we are choosing. So now note that we are doing a transformation of this kind, that phi is going to e to the power I theta phi. So this kind of transformation is called global transformation, global gauge transformation, because this theta you can see in the phase, theta is a constant. It does not depend on the space-time coordinates. So as you can see, if you substitute this thing, you can see that this Lagrangian remains invariant, means it doesn't change. So basically this is a symmetry of the Lagrangian. So this transformation is a symmetry of the Lagrangian. But if you transform this thing in this classical vacuum, you can then see that this solution changes. So basically it no longer be a symmetry for the classical vacuum. So this is called the spontaneous symmetry vacuum. Means the symmetry of the Lagrangian doesn't reflect on the symmetry of the classical vacuum you have chosen. So this is called the spontaneous symmetry vacuum. And now corresponding to every spontaneous symmetry vacuum, there is a Goldstone field or Goldstone boson. So how we determine that? So basically as you can see, this is the Lagrangian. Now what we do, phi is a complex scalar field, so we decompose in the two real fields, that is phi 1 and phi 2, like this. So the potential can be written as this thing very simply in terms of phi 1 phi 2, and the Lagrangian also can be written in terms of phi 1 phi 2. Just substitute these values, so ultimately you will get this expression. Now I want to write it like a matrix form. So basically what we define a capital phi to be a column matrix of phi 1 phi 2. Then the Lagrangian can be written like this. and the classical vacua are given by this thing, phi transpose phi is a square. Similar thing, just written in various forms. So basically now what we are doing, we are choosing again one classical vacuum, that is we are choosing this. So this is phi 1, this is phi 2, and you see that this satisfies this equation. So basically this is a classical vacuum. There can be others, so we are choosing one particular classical vacuum. Now we are expanding the field phi around the chosen vacuum like this. So basically here eta is a small fluctuation. Then you can basically write it as matrix form: phi 2 phi 1 phi 2, phi vacuum to be 0a, and eta to be eta 1 eta 2. So by comparing, you can get phi 1 to be eta 1 and phi 2 to be a plus eta 2. Now just substitute this phi 1 phi 2 values in the potential. What we will get? You will get this just phi 1 square, this eta 1 square, phi 2 square is a plus eta 2 whole square. So basically you get this term minus a square. Basically a square will cancel, and what you do, as eta 1 eta 2 are small fluctuations, you neglect the square terms, then you get 2a eta 2 square whole square. So from this you get potential to be as this. Now we generally know the potential generally in field theory looks like this thing. So here the coefficient of half fields, the field square is mass. So basically what we get, the mass of the eta 2 field to be root over of that will be m square I square. So this will be m square, so mass will be square root of this thing. But you can see in the potential there is no eta 1 square term, so mass of the eta 1 field is 0, and we call this eta 1 field, that massless scalar field, to be Goldstone field. Goldstone field, or the Goldstone boson corresponding the particle, it is called Goldstone boson. And there is a theorem called Goldstone theorem that says that if the Lagrangian is invariant under a continuous transformation but not the classical vacuum, then the spontaneous symmetry breaking occurs followed by massless boson. That is called Goldstone boson. So if there is a continuous spontaneous symmetry breaking of a continuous symmetry, then there should be one Goldstone field, and here is the Goldstone field eta 1 corresponding to this global symmetry, that is breaking, global gauge symmetry. Okay, so now we will study another important thing, that is local gauge invariance. Whatever we have told till now, that was regarding global gauge symmetry or breaking of the global gauge symmetry. Now we will talk about local gauge symmetry. So basically what is local? So previously we have seen that phi we transform as e to the power I theta phi, and where theta is a constant. But what we do now, we replace it by alpha x, where alpha x, now alpha depend on the space-time points. So it depends on the space-time points. So it is no longer a constant, it becomes a function in space-time. Okay, and it can be any arbitrary function. There is no restriction on alpha x. Now we have this Lagrangian again. So if phi transforms this way, phi dagger will transform this way, and you can see this del mu phi term, derivative term, transform this way. So there is a piece of del mu alpha that was not there because theta, there is a constant theta. Theta is not a function of space-time points, that's why the derivative term was 0, but here it is not 0. So this term basically breaks the local gauge invariance, so the theory is not locally gauge invariant. So but we want local gauge invariance. Okay, so if we want local gauge invariance, we have to modify the derivative. That is the only way. So basically we have to replace this partial derivative by some modified derivative that we call covariant derivative. So capital D mu is called the covariant derivative. And we want such type of transformation, like you see that this transform as this, but we don't want this term. So basically we want only this term. So we want d mu phi transform like this term. Okay, so to do that we construct the covariant derivative as this. So now you see there is a term e mu. So what is e mu? So to form this covariant derivative, we must introduce a vector field a mu such that the unwanted term del mu phi is cancelled. So we have to introduce a new vector field, or this field is called gauge field. This vector field is called gauge field. So otherwise we can't do this cancellation of this unwanted term. So if we impose the theory to be locally gauge invariant, we must have to introduce a new field, new gauge field. So we are not doing by hand, it is coming through the theory itself if we invoke the local gauge invariance. And the mu must transform as this thing. You may check that if it should transform like this, otherwise the theory will not be gauge invariant, means this thing will not transform as this. So this is called the gauge transformation of the gauge field. So mu should transform like this thing. So now you just the modified Lagrangian will be, you just replace the partial derivatives term by d mu and potential remains same. Okay, the potential is always, you see, potential always remains same. Potential term is invariant under the transformation because potential is a function of phi dagger phi. So for phi dagger phi, this is always same because it is e to the power I and e to the power minus I, so basically that is 1, so it will be always same. So there is no change in potential term, and we are introducing a new term, that is the kinetic term for the gauge field. So basically it includes the dynamics of the gauge field. Now we are adding this term by hand. So this is basically dynamics of the gauge field. Okay, and this F mu nu, that is called the field strength tensor. This is called field strength tensor of the gauge field mu, and it is given by this. And now note that this mu gauge field is abelian. What do you mean by abelian? That the strength tensor is given by this. If it is not abelian, there is some term, extra term. Basically there are some extra term involving the gauge fields, and there are many more consequences of that thing. Okay, but I will not go into that. So, and one important thing, you cannot add any mass term to the like this term. So this is a mass term of the gauge field, but if you add mu kind of term, this will break the gauge invariance. This will again break the gauge invariance because mu transform as this, again del mu alpha type of term comes, so the Lagrangian will not be same, so the local gauge invariance will be broken. So you can't add the mass term to the this gauge field, so this gauge field is massless, so mu is massless. Okay, so these were the necessary prerequisites to understand Higgs mechanism. Now we will do the Higgs mechanism. So basically what we will do, we will do abelian Higgs mechanism. As I already mentioned, why abelian? Because here the gauge field we are talking about is basically abelian kind of gauge field, so it is not non-abelian, because non-abelian case is much more complex. It is very much simple. So to understand what is basically Higgs mechanism, so our goal is to understand what is Higgs mechanism. Okay, so to start the Higgs mechanism, we first write the complete Lagrangian of the locally gauge invariant complex scalar field theory. So this is the complete Lagrangian, you can see. Now you can see that f mu nu is I am written as a function of a, it is nothing but it is del mu a nu minus del mu m. Means basically a for a field, I am mentioning that it is for the a mu gauge field, because we need some other thing I will mention, so just follow what I am saying. So first we will write the scalar field again as this thing in terms of two real fields phi1 phi2. Now it is very simple that you apply the d mu phi to this expression phi1 plus I phi2, you end up with this expression. Then you just take d mu phi star d mu phi, and basically you will get this thing. So basically here square means nothing but it is the shorthand. This one is this thing times the upper indices. Okay, similarly for these terms. Now you expand the whole thing, you will end up with this expression, and you can write the full Lagrangian in terms of phi1 phi2 fields. So you can see that, and okay, let's do the same expansion and the chosen vacuum that we have done previously, phi1 to be eta 1 and phi to be a plus eta 2. So eta 1 eta 2 are small fluctuations, remember, around the classical vacuum we have chosen. And now we want to write the Lagrangian in terms of eta 1 and eta 2 fields. So basically this is the expression. Now what we do, basically eta 1 eta 2 are small fluctuations, so we neglect any terms higher than second order, like third order, fourth order term we neglect, and we end up with this Lagrangian that L quad means all terms are quadratic in fields. You see, this term is quadratic in eta 1 field, this term is quadratic in eta 2 field, this term is quadratic because mu plus and eta 1 term is coming. This is also quadratic in gauge field mu. This is also quadratic in eta 2 field, and this is also quadratic in mu fields because these are derivative of this kind. So multiplication of these two will give the kinetic term that is also quadratic. Now you see the interesting thing, and so this is the kinetic term of eta 1, that is fine. This is also fine. This is kinetic term of eta 2, this is also fine. This is the kinetic term of the gauge field, this is also fine. So you can see this one term that involve that eta 1 and mu field. So this term is called the mixing term. So this is called the mixing term, that the scalar field eta 1 and the gauge field mu mixes. So this term is the mixing term. And this term, this is the mass term of eta 2, mass term of the eta 2 field. This is also fine, but you see this term, so this is basically mass term of mu. So what is the mass of this gauge field? It is q times a. So when we do these steps, basically we chose one vacuum and expand. Basically what we ended up with a massive vector field, but we have started with a massless vector field here. But when we do this process, we end up in massive vector field. So now do the degrees of freedom calculation. So in the Lagrangian in 33, so basically this Lagrangian we are talking about what is the total degree of freedom we want to calculate. So basically you can see there is one massless vector field, so there are 2 degrees of freedom corresponding to that, and there are one phi 1 field and one phi 2 field. So there is total 4 degrees of freedom in Lagrangian 33. Now consider the Lagrangian in 36, means this Lagrangian. So what are the degrees of freedom? You have one massive vector field. So for massive vector field, the degrees of freedom is 3, and you have one scalar field, so eta 1 and eta 2. So you ended up with 5 degrees of freedom. But this can't be possible. This is of 4 degrees of freedom, and this is the same Lagrangian. Just you have done this process, you got 5 degrees of freedom. Okay, so this is not a physical thing, so we have to do more calculation to remove 1 degrees of freedom basically. So basically what you have to do, you have to remove one of the scalar fields. That's eta 1, eta 2. You have to remove one of the scalar field. And which scalar field you have to remove? You have to remove the Goldstone field. That massless field. And what is the massless field? Eta 1. So you have to remove this eta 1 field by some proper calculation, and so that the actual degrees of freedom is 4, not 5. It can't be 5. It has to be 4. So this Lagrangian, so see this term is this term, this mass term of beta 2, this kinetic term of the gauge field, these are same. These 3 terms you have to see. We can write this 3 term. You have to do some algebra, and you can write this is like this as a factors. So now what you do, you define a new gauge field. This is one of the very important thing. You define a modified gauge field, not new. So what you do, you modify the mu field by the Goldstone field. So this is the important thing. You invoke a new gauge field or modified gauge field where you adding this eta 1, that is the Goldstone field, and you can see now the strengths are corresponding to the B gauge field. Okay, that's why I have kept in bracket A, B. So if you calculate this, you can see these are partial derivatives. So basically these partial derivatives commute, so this term will cancel effectively. So this kinetic term remains same for B field, also for A field. Okay, so you can see by this process, this Goldstone field is absorbed in the gauge field. So by this thing you remove basically the Goldstone field. So basically the Goldstone field absorbs into this H field. So it is there is a fancy name of this process, that the massless Goldstone field eta 1 is completely eliminated or said to be eaten up by mu. So basically eaten up by mu means mu eats this Goldstone field, that massless field. Now you can identify this to be a very important transformation that we have talked about, that this type of transform, this is a gauge transformation, if you notice. So what was our gauge transformation? That mu transform to mu plus 1 by q del mu phi, where phi is the gauge function. Now here this is itself, means this eta 1 field itself a gauge function for this transformation. So the Goldstone field itself is the gauge function. Now then we have to do the gauge transformation of scalar field as well. Means we have to do the gauge transformation of the whole Lagrangian. So we have to do this type of thing, and here you see we have e to the power I alpha x before. Now it is nothing but I by a eta 1 of x, because the gauge function is eta 1 divided by a from this. Now as you know, this eta 1 is a very small fluctuation, so you can approximate this exponential by this linear order term, and you just write phi to be in terms of the real fields here also. Then you just expand and you just take the linear order, you neglect all the second order and higher order terms. So basically you ended up with phi 1 prime, the transformed real scalar field. First is 0 basically in linear order, and the second scalar field you got a plus eta 2. So what you do the whole gauge transformation of this thing, and you end up with this final Lagrangian. So you have kinetic term of eta 2 field, you have the massive vector field b mu with mass qa, and this is another term, you can say mixing kind of term involving b field and eta 2 field. This is the mass term of eta 2, so mass is root 4 lambda a square, and this is also an extra term you got, and this is the kinetic term of b field. So what we finally get? So finally we have a massive vector field b mu with mass qa, and one surviving real massive scalar field eta 2 with mass eta 2 with mass root 4 lambda a square. Then the total degrees of freedom. Now see, there is one massive vector field b mu, so degrees of freedom is 3, and one scalar field eta 2, so degrees of freedom is 1, so total degrees of freedom is 4. So we got back the initial degrees of freedom, that was 4 in this Lagrangian, but in this Lagrangian it appears to be 5, but it is not 5. By this thing you make it to be again 4. So that is the process. This is called the Higgs mechanism. This whole process is called Higgs mechanism, and this surviving scalar field, that is eta 2 is surviving, this field is called Higgs boson or Higgs field. So this eta 2 field is called Higgs field or Higgs boson. So this was the basic example to demonstrate what Higgs mechanism is. So basically the Higgs mechanism, why it was introduced, basically in standard model, if you know, there are two particles, that is WZ boson. These are the carriers of weak interaction, So what happens, from normal theory it appears that this should be massless, it have to be massless, but in experiments it has found that these have mass, these are massive, and the masses are quite large. Okay, not that small tiny masses. So so we have to explain it by theory. So what Higgs did, Higgs proposed this mechanism by which the Goldstone fields of that theory of standard model basically uh, eats the scalar fields or the Goldstone fields and gives them mass. So basically W and Z bosons acquire mass from that Higgs mechanism, and it basically matches with the theory. So this was the main motivation of Higgs to propose this mechanism. Okay, so this was the Higgs mechanism. So in one line, Higgs mechanism is like, if you have two scalar fields plus one gauge field that is massless. Okay, this is massless. So what you do Higgs mechanism, and you end up with one scalar field plus one massive gauge field, and this one scalar field, that surviving scalar field, is called Higgs field or Higgs boson. So this is the whole Higgs mechanism shortly. So I hope you like the video. All this calculation is done by me only, so if there is any mistake in the calculation, please let me know in the comment section. Thank you.